Algorithms often feel chaotic when you watch them execute. A blur of moving parts, shifting values, and rapidly updating memory states. This is exactly why technical interviews induce panic. Staring down a sliding window, binary search, or fast and slow pointer problem, the execution looks completely disjointed. Developers try to survive by memorizing the mechanics, the exact syntax for when pointers increment, pause, or jump. But that syntax-first approach is incredibly fragile. The moment a problem introduces a slight twist or an edge case you didn't memorize, the entire mental model collapses, and the code fails. To build algorithms that survive edge cases, you have to stop tracking the pointers and start tracking the logic underneath them. You need to identify the algorithmic invariant. An invariant is simply a strict logical statement about your data that must be true at the start and true again at the end of every single iteration of a loop. By focusing strictly on keeping that mathematical statement true, the pointer movements define themselves. You stop guessing, and you start engineering a system that guarantees a correct result. This diagram shows the simplest iteration, transferring discrete items between locations. We start with 10 square blocks in box A and an empty box B. The invariant here is simple. The total number of items across both boxes must always equal 10. Every invariant-based loop operates on a strict three-phase lifecycle: held, broken, and restored. Before the loop even begins its first iteration, the statement is held. The mathematical truth is confirmed before a single variable is touched. Then, the intermediate work begins. We pop an item out of box A. It's now suspended in memory. Box A has 9 items, and box B still has 0. At this exact fraction of a second, the total visible count is 9. The invariant is broken. The system is temporarily in an invalid state. But the iteration isn't finished. We append the item into box B. The visible total is 10 again. The invariant is restored. The loop has successfully repaired the mathematical truth, making it safe to trigger the next iteration. The middle of an algorithmic update will almost always be messy. Variables shift rapidly and the logic breaks. What makes an algorithm correct is that its internal architecture mathematically forces a complete restoration of the truth by the final line of the loop. Once you understand that cycle, you can start applying it to complex data structures. Most multi-pointer algorithms rely on one of 4 specific invariant shapes. This graphic demonstrates shape 1, the finished region, which drives algorithms like merge sort. 2 sorted arrays are merging into the single output array below them, highlighted in green. The invariant dictates that the green section contains the correct sorted sequence built up to this point. As pointers evaluate the next numbers, 5 and 4, the boundary of certainty is temporarily compromised. By selecting and appending the 4, the algorithm safely takes one step forward. The green boundary expands to encompass the new element, and the invariant is restored. This next diagram illustrates shape 2, remaining candidates. Think of binary search. The yellow highlight covers the entire array, representing our active candidate space. We are looking for 11, but our current midpoint is 9. The invariant states that if the target answer exists at all, it mathematically must reside inside this highlighted range. Testing the midpoint of 9 briefly breaks our logic, but because 9 is too small, everything to its left is also too small. Striking out that impossible half restores the invariant by tightly constricting our search bounds. Neither of these algorithms guesses where a pointer should go. They simply advance a boundary of absolute certainty, one step at a time. This visual maps out shape 3, the active state, commonly seen in sliding window problems. The green bracket spans over a set of unique characters. The active state invariant requires the current live window to strictly satisfy a core rule, in this case 0 duplicates, before the algorithm processes it. Expanding the right pointer brings in a duplicate character. The rule breaks, and the bracket flashes red. To repair the state, the left pointer must contract inward, dropping characters until the duplicate is gone and the window is valid again. Finally, we have shape 4, variable relationships. This diagram models a linked list with a slow pointer and a fast pointer, connected by a dotted line. Unlike the previous shapes, this invariant isn't managing a spatial zone. It manages a strict mathematical ratio. The slow pointer moves 1 node, and the fast pointer moves 2. By perfectly preserving that 2-to-1 speed ratio step by step, The algorithm builds the mathematical foundation required to detect infinite cycles. Mastering these specific shapes gives you a repeatable framework. You map complex, dynamic data constraints into predictable, self-repairing state machines. Zooming out, the pattern is remarkably consistent. At a micro level, all algorithms are inherently messy, broken, and chaotic during the intermediate update step. True algorithmic correctness does not require every intermediate line of code to be flawless. It relies exclusively on the absolute guarantee that the state will be restored by the end of the loop. This is what the life cycle looks like when applied across all 4 algorithmic shapes simultaneously. Whether you are merging, searching, sliding, or tracking, the core mechanism is identical. So the next time you face a technical challenge, stop asking yourself the mechanical question of how the pointer should move. Instead, ask the operational question: what must be true again once this iteration finishes? When you define that state invariant clearly, the logic writes itself. The constraints of the invariant will automatically dictate exactly when and where a pointer needs to shift. Prioritizing invariant reasoning over syntax memorization elevates you. It is the exact threshold where you transition from merely typing code to architecting mathematically sound systems.